The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, last time we started in on a discussion of entropy, a new topic, and I started out by writing out some somewhat verbose written descriptions that had been formulated that indicate certain limitations about things like the efficiency of a heat engine and what can be done reversibly and so forth. And these verbal descriptions lead to some pictures that I put up, and I'll put up again, about how you might try to accomplish something like run an engine or move heat from a colder to a warmer body, and what some of the limitations are on things like that. I'll show those again, but what I want to do mostly today is try to put a mathematical statement of the second law in place that corresponds to the verbal statements that we saw last time. So just to review what we saw before, we looked at a heat engine where there's some hot reservoir at some temperature T1, and it's connected to an engine running in a cycle. We could write the work that we generate that comes out as negative W. And then there's a cold reservoir. At some lower temperature, T2. So the way I've got things written here, Q1 is positive. Heat's flowing from the hot reservoir to the engine that runs in a cycle. Work is coming out. A positive amount of work is being generated and is coming out. So minus W is positive. And this minus Q2 is positive. That is, heat is also flowing into a cold reservoir. All right, and what we saw last time is that this was necessary to make things work, this part of it in particular. You couldn't just run something successfully in a cycle and get work out of it using the heat from the hot reservoir without also converting some of the heat that came in to heat that would flow into a colder reservoir. All the heat couldn't get successfully converted into work. Right? That would be desirable, but it's not possible. And similarly, if we try to run things backward and build a refrigerator, so now we have our cold reservoir, and we're going to remove heat from it and pump it up into a hot reservoir. And to do this, we saw that you have to put work in, right? You can't just remove heat from a cold reservoir, move it up to a hot reservoir without doing some work to accomplish that. So here, Q2 is greater than 0. The work is greater than 0. And minus Q1 is greater than 0. That is, heat's flowing this way. Okay? So these are just the pictures that we saw last time. And then we had some statements of the second law of thermodynamics that I won't rewrite up here, but for example, Clausius gave us the statement that it's impossible for a system to operate in a cycle that takes heat from a cold reservoir, transfers it to a hot reservoir, that is, acts like a refrigerator, without it at the same time converting some work into heat. Work has to come in to make that happen. And we had the similar statement by Kelvin about the heat engine that required that some heat gets dumped into a cold reservoir in the process of converting the heat from the hot reservoir into work. Fine. Now what I want to do is put up a specific example of the cycle that can be undertaken by, inside here in an engine, and we can just calculate from what we've already seen of thermodynamics what happens to the thermodynamic parameters and see the results in terms of the parameters including entropy. So let's try that. So the engine that I'm going to illustrate is called a Carnot engine. And the cycle it's going to undertake is called a Carnot cycle. And it works the following way. We're going to do pressure volume work. So this is something that by now you're pretty familiar with. So we're going to start at 1, go to 2, and this is going to be an isotherm at temperature T1. And all the paths here are going to be reversible. So that's our first step. Then we're going to have an adiabatic expansion. So this is an isothermal expansion. Here comes an adiabatic expansion to point 3. So at this point, the temperature will change. Then we're going to have another isothermal step, a compression. To some point 4. So this is an isotherm at some different temperature T2, a cooler temperature, because this was an expansion. We know at an adiabatic expansion, the system's going to cool. And now we're going to have another adiabatic step, an adiabatic compression. And that's it. That's going to take us back to our starting point. So that's our cycle, right? Of course, there are lots of ways we could execute the cycle. But this is a simple one, and these are steps that we're all familiar with at this point. Right? So this is the picture, and this is the cycle that undertakes it. So let's just look step by step at what happens. So going from 1 to 2, it's an isothermal expansion at T1. So delta U is Q1, we'll call it, plus W1 for the first step. Going from 2 to 3, that's an adiabatic expansion. So Q is equal to 0 in that step. And delta U is equal to what we'll call W1 prime. So we'll use W1 and W1 prime to describe the work involved, the work input during the expansion steps. Step 3 to 4, isothermal compression. Delta U is going to be Q2 plus W2. And finally, we're going to go back to 1. We're going to close the cycle with another adiabatic step. Q is 0. Delta U is W2 prime. Right? Now, the total amount of the work that we can get out is just given by the area inside this curve. Right? we'll call it capital W. It's just minus the sum of all these things because, of course, these are just defined as the work done by the environment to the system. So it's minus W1 plus W1 prime plus W2 plus W2 prime. Right? The heat input is just Q1. And we'll define that as capital Q. And I just want to write those because what I really want to get at is what's the efficiency of the whole thing. And in practical terms, we can define the efficiency as the ratio of the heat in to the work out. We would like that to be as high as possible. Right? Okay, so it's just capital W over capital Q, which is to say it's minus all that stuff over Q1, right? Now, the first law is going to hold in all of these steps, and we're going around in a cycle, right? So what does that tell us about a state function like U? What's delta U going around the whole thing? I'm on a chorus in the answer here. What's delta U? Excellent. MIT students, yes. Okay, so the first law, we know that going around the cycle, the integral of delta U is 0. Right? And that has to equal Q plus W summed up for all the steps, right? Which is to say Q1 plus Q2 is equal to minus W1 plus W1 prime plus W2 plus W2 prime, right? So that means we can rewrite this efficiency. We can replace this sum by just the sum of Q1 plus Q2, right? So efficiency is Q1 plus Q2 over Q1, right? Or we can write it as 1 plus Q2 over Q1. Okay? Now, that already tells us what we know, which is that the efficiency is going to be something less than 0, right? Because we've got 1, and then we're adding Q2 over Q1 to it, but we've got negative Q2 as a positive number, right? Heat is flowing this way. So Q2, the heat in this way, is negative, right? Q2 over Q1 is negative. Q2, of course, is positive. That's heat flowing from the hot reservoir to the engine, right? So that efficiency is something less than 1, and we'd like to figure out what that is, right? So let's just state that. Okay. Well, now let's go back to each of our individual steps and look based on what we know about how to evaluate the thermodynamic changes that take place here. Let's look at each one of the steps and see what happens. So, for 1 to 2, it's isothermal. And now we're going to specify, we're going to do a Carnot cycle for an ideal gas. It's an ideal gas. It's an isothermal change. What's delta U? You know, it's like lots of choruses and all sorts of things that you sing. They're always the same. What's delta U? Right. delta U is 0, and it's also equal to this, so that says that Q1 is the opposite of W1. It's an isothermal expansion, so dW is just negative p dV, so this is just the integral from 1 to 2 of p dV, right? And it's an ideal gas, isothermal, right? RT over V, we're going to make it for a mole of gas, so it's R times T1, right? And then we'll have dV over V, so that's just the log of V2 over V1. Right? Let's have 1 mole, n equals 1. Okay. 2 going to 3, that's this, it's adiabatic, right? So delta U is just equal to the work, but we also know what happens because the temperature is changing from T1 to T2, right? So delta U is just CV times T2 minus T1, right? du is CV dt, it's an ideal gas. Okay. And that's equal to W1 prime. Okay? Now, this is a reversible adiabatic path, so there's a relationship that I'm sure you'll remember. Namely, T2 over T1 is equal to V2 over V3. Don't be confused by the subscripts. We're talking about quantities both starting at 2 and going to 3. Right? So it's V2 and V3. They're different volumes. The temperature, though, at 2 is the same as it was at 1, so it's still at T1. And this temperature is T2. Anyway, T2 over T1 is equal to V2 over V3 to the power gamma minus 1. So we're going to kind of store that for the moment. Now, going from 3 to 4, right? So we have another isothermal process for an ideal gas. So I won't try to make you sing again so soon. Delta U is 0. And so just like here, now Q2 is minus W2. That's integral going from 3 to 4 of P dV. So it's RT2, right? Now we're at a lower temperature, times the log of V4 over V3, right? So that's our work in this path and heat. And finally, going from 4 back to 1, so we've already seen that Q is 0. So we know that delta U is just CV times T1 minus T2. Now we're going from T2 up to T1. And this is equal to W2 prime. And now, just like we had before, again, we've got a reversible adiabatic path. So T1 over T2 has to equal V4 over V1 to the gamma minus 1. Okay? All right. Now, if this is the case, of course, this is just the inverse of this, right? So this just must be the inverse of this, right? We can combine these two to see that V4 over V1 must equal V3 over V2. Okay, so now we have a relationship between the ratios of these volumes that are reached during these adiabatic paths. Right? Okay. Now, let's just look at our efficiency. So we saw that efficiency is 1 plus Q2 over Q1. Let's just use our expressions that we've found for Q2 and Q1, right? We're going to have Q2 over Q1. R is going to cancel. We're going to have the ratio of temperatures and the ratio of these logs, right? So it's T2 over T1 times the log of V4 over V3 over the log of V2 over V1. But we just derived this relationship between these volumes. And this, of course, tells us that V4 over V3 is V1 over V2, right? I'm just inverting these. So here it is. Here's V4 over V3. Oops, sorry. V2 over V1. This is equal to the inverse of this, right? So the ratio of the logs is just -1. So this is just, sorry, I forgot the 1 here. 1 plus this, but this is the same as 1 minus T2 over T1. That's our expression for the efficiency. All right. Isn't that terrific? Now, we have an expression. We can figure out the efficiency. All we need to know is the temperatures. What's the temperature of the hot reservoir? What's the temperature of the cold reservoir? We're done. Right? That's the efficiency. As we expected, it's less than 1. And of course, if we build an engine, we want it to be as high as possible, as close to 1 as possible. What that means is we want to run the hot reservoir as hot as possible and the cold reservoir as cold as possible. In principle, this value, this efficiency, can approach 1 as the low temperature approaches absolute 0, right? If this were to be an absolute 0 Kelvin, right? Then we could have something, wait a minute, sorry, it's T2. As T2 goes to 0, the cold reservoir, then this goes to 0, and then our efficiency approaches 1. Right? So that would be the best we can do. And that basically makes sense, right? The whole thing is being powered by sending heat from the hot to the cold reservoir. Right? The colder that cold reservoir is, the hotter that hot reservoir is, the better off we are, the more work we can get out of it. The closer the efficiency will get to 1. Okay? So, in some sense, the first law would suggest you can sort of break even, right? That is, it gives us a relationship between energy and work and heat, might suggest that you could convert all the work to heat. The second law says that really you can't do that. The only way you could possibly contemplate it is to be working at absolute 0 Kelvin. Guess what the third law is going to tell us? You can't get to 0 Kelvin. We'll see that shortly, right? But this is the closest you could come, at least by trying to do that, to having your efficiency approach 1. Okay. Now, we've seen that Q2 over Q1 is equal to negative T2 over T1, right? So let me just rewrite that as Q1 over T1 is minus Q2 over T2. Or in other words, Q1 over T1 plus Q2 over T2 is 0, right? But Q1 and Q2, each one of those is just the integrated amount of heat that was transferred going along a reversible constant temperature path, which means that, you know, Q1 and over T1, that's this delta S thing that we saw before, right? I mean, what we can say about this is it's saying that if we go around in a cycle and look at dq reversible over T, it's 0, right? Because that's what these quantities are. Okay. Now, of course, we can run the engine backward and build a refrigerator, right? And if you've got your lecture notes from last period, your 8-9, what are labeled 8-9 lecture notes, I made an attempt to define something which was a little bit misguided. And so instead of defining efficiency the way you've got it written there, I'm going to define what's called something different for a refrigerator, which is called the coefficient of performance. Okay? So it's the following. Let's see. So we can define the coefficient of performance, written as eta, as Q2 over minus W. In other words, it's how much heat can we pull out of the cold reservoir, right, for whatever amount of work that we're going to put in order to do that. Well, of course, we'd like that to be as big as possible. But of course, this is just Q2 over minus Q1 plus Q2, right? That, just to be clear here, so it's heat extracted over the work in, right? So let me just rewrite that as, I just want to divide by Q1 everywhere. So I'm going to write this as Q2 over Q1 over minus 1 plus Q2 over Q1. And I want to do that because we know that Q2 over Q1 is negative T2 over T1. So this is negative T2 over T1 over negative 1 minus T2 over T1. I can cancel those. And then I'm going to multiply through by T1. So this is just going to be T2 over T1 minus T2. That's our coefficient of performance. Right. Okay, so it's a measure of how well we can do to run the refrigerator. So, what the second law is doing in words, it's putting these restrictions on how well or how effectively we can convert, heat into work in the case of the engine, or work into heat extracted in the case of a refrigerator, right? And it follows qualitatively from just your ordinary observations about the direction in which things go spontaneously, right? You know the heat isn't going to flow from a cold body to a hot body without putting some work in to make that happen, right? And so we'll be able to follow that further and see really how to determine the direction of spontaneity for a whole set of processes, really in principle for any process, right, when analyzed properly. Okay, so the first step to doing that is I want to just generalize our results so far for a Carnot cycle, right? You might think, well, okay, but this is a pretty specialized case, right? We've formulated one particular kind of engine and seen how we can analyze what it does, right? Come up with relations that seem of value for efficiency and other quantities, right? How general is it? Right? Well, let's take a look. So what I want to do is make a new engine which really just consists of two engines side by side. One is our Carnot engine, as we've seen it, and the other is just any other reversible engine, right? So generalize our Carnot engine results. So let's take our hot reservoir and draw it bigger. We know it has to be big anyway, since we can extract heat from it without changing the temperature. And on this side, we're going to write out an engine, and we're going to say this is a Carnot engine. So on this side of it, we're going to have Q1 prime, and we're going to have W prime, and we're going to have Q2 prime, and we're going to draw the arrows in the positive direction in these cases, or in the defined directions, I should say. Here's our colder reservoir. Okay, so here's just an engine that, like what we've already seen, and I'm going to specify that this is a Carnot engine, which is to say all the results that we just derived hold for this case. And side by side, we're going to run another engine. So it's got Q2, and it's got a cycle W, and it's got Q1. So this is some other engine that runs using reversible processes. Okay? So I can define the efficiency of each one of them, right? The efficiency for the one on the left is minus W over Q1. The efficiency prime for the one on the right is minus W prime over Q1 prime. Now I want to just assume that in some way they're different. So let's assume that epsilon prime is greater than epsilon. Okay? So in other words, this engine is running less efficiently than my Carnot engine. Right? It's also a reversible engine. Right? Now, since it's reversible, we can run it forward or backward. Right? So we could run this one backward. Right? And we could use the work that comes out as the input. Well, sorry, use this work that comes out of the one on the right to run this one backward, right? Which is to say we'll move heat from cold to hot. So use work out of right-hand side to run left-hand backward. Right? Why not? We need work to come in. We might as well get it from here. Right? Okay. So, the total work that we can get out must be 0 out of the whole sum of them, right? After all, we're taking the output work that we get from the right and using it all to drive the left, right? So that means that minus W prime must equal W, right? And W is greater than 0, that is, in this one, we have the environment doing work on the system, right? Okay. Now we've assumed that epsilon prime is greater than epsilon, so we can just write out what those are. Minus W prime over Q1 prime is greater than minus W over Q1, right? But we know that minus W prime is the same thing as W, right? So W over Q1 prime is greater than minus W over Q1, right? Which is the same thing, just to be a little bit maybe pedantic, as W over minus Q1. And the only reason I'm writing that is to illustrate that this says that Q1 must be less than Q1 prime, right? Since Q1 is less than 0, right? Remember, this one's running backward. We're pumping heat up, right? Q1 prime is greater than 0. It's running as an engine. It's taking heat from the hot reservoir, right? Well, that's interesting. That says that minus Q1 prime plus Q1 is greater than 0. Well, it's a pretty interesting result. There's no work being done out of the whole thing, right? This is providing work that's being used in here, but if you take the whole outside as the surroundings and this whole thing as the system, right? No net work. These things cancel each other. And yet, heat's going up. How'd that happen? Well, it happened because we clearly must have a faulty assumption underlying what we've just done, right? This can't possibly be true, right? So this is impossible. So what this says is the efficiency of any reversible engine has to be 1 minus T2 over T1. Okay? It's not a result that's specific to the one cycle that we put up, right? And you know, you could have a reversible engine with lots and lots of steps, but you could always break them down into some sequence of adiabatic and isothermal steps. So you know, your cycle, you know, you could have a whole complicated sequence on a PV diagram of steps, right? Going back, as long as it's reversible, you know what the efficiency has to be. And in principle, you could break it down into a bunch of steps that you could formulate as isothermal and adiabatic. They might have to be formulated as very small steps in order to do that, but you could. Okay? what this says, too, is this result that we found, right? Now, of course, that's our integral ds is 0. It's general, right? Entropy S is a state function, generally, right? Now remember, we went through before how it's a state function, but to calculate it, you need to find a reversible path along which you can figure this out. But the fact is it's a state function in a general way, right? Okay. Now, if we go back to our Carnot cycle, which is a set of reversible paths, it's useful to compare this to what happens in an irreversible case, right? In a real engine, of course, you can approach the reversible limit, right? Every step won't be perfectly reversible. And of course, it's not hard to see what happens. You know, let's just take our reversible engine and modify it a little bit, right? Let's imagine that instead of all the steps being reversible, let's just put in one irreversible step, right? Let's do this. Instead of this reversible isothermal step, let's make it an irreversible isothermal step, right? You know, we could have a different isothermal step. Of course, in the reversible case, you're always pushing against an external pressure which is essentially equal to the internal pressure, right? Let's not do that. Let's imagine maybe instead we just immediately dropped the pressure and let the system expand against the lower pressure, right? Now we know we're going to get less work out of it in that case. You've seen that before, right? And the work in this case is the area inside here. The work in this step is just the area under this curve. So in some way, we're going to have a difference here between the irreversible case and the reversible one, right? Okay. So if we do that, then what I want to do is just see what happens to dq over t. So in our irreversible engine, right, 1 to 2, what we know for sure is that minus w in the irreversible step is going to, that's the work out extracted in that step, is going to be smaller than minus w in the reversible case, right? So w irreversible is bigger than w reversible. And of course, in either case, delta u is q plus w, so it's q irreversible plus w irreversible. But of course, u being a state function, it's the same in either case. So it's the same as q reversible plus w reversible, right? And we've just seen that this is bigger than this, but the sums are equal. So this has to be less than this. Q irreversible is less than q reversible, right? In other words, an irreversible isothermal expansion takes less heat from the hot reservoir than a reversible one does. Makes sense, right? Because you know you get less work out, and delta U is the same, right? So it must be that less heat got transferred, right? So the expansion against lower pressure draws less heat from the hot reservoir, right? So now let's look at the efficiency of our irreversible engine. So it's 1 plus Q2. Now, Q2 was in this step, and we're going to leave that reversible, right? But Q1 is irreversible, right? And this is got to be less than 1 plus Q2 reversible over Q1 reversible, which is to say it's less than our efficiency in the reversible case, right? Why? This is smaller than this, but it's a negative number, right? So this negative number has a bigger magnitude than this negative number, right? We're subtracting them from 1, and they're less than 1. So this is bigger than this, right? And all we know about this is that it's really for some irreversible step, right? All we really needed to know about it is that this is smaller, right? So it's going to be the case for any irreversible engine. And that's the point. So it's that when irreversible efficiency is lower than the reversible one, right? But of course, since we saw that this is smaller than it was in the reversible case, right, we can also write that dq irreversible over T is less than dq reversible over T, right? Which is to say, if we go around a cycle for dq irreversible over T, that's less than 0, right? It's only in the reversible case that dq over T around a cycle is equal to 0. So to write that in a general way, it's actually formulated by Clausius. Going around in a cycle, the integral of dq over T is less than or equal to 0, right? Never greater. Okay? Okay. What we'll see shortly is that this will allow us to see that for an isolated system, the entropy never decreases. It only can go up, right? And that's what, and in fact, any spontaneous process will make it go up, okay? Only in the case of reversible processes. Of course, then you can see that this will be 0, right? Anything else, which is to say any spontaneous process, it'll be less than 0. Right? All right, we'll see that next time, and then we'll generalize in a broader sense to look at the direction in which spontaneous processes go.